But as soon as there is a fracture, then the magnitude and the intensity of signal will further get reduced. By using an algorithm and comparing the signals which are being picked up at sensors, we can come to a conclusion whether there is a discontinuity in the track or not. Then UBRT system is also being tried on Indian Railways. Then optic fiber cable-based acoustic system, it is also under trial. Now in our proposed concept, if we see the wave pattern, in case of unfractured rate, at any point of time, it may look something like this. As soon as there is a rail fracture, we will find that the wave pattern will change because of the discontinuity, and then this magnitude and amplitude will get reduced. Basically, the principle of working is that in case of when a mechanical wave propagates through two mediums, then the velocity in iron is much higher as compared to velocity in air. And amplitude in air is reduced as compared to in iron whenever there is a discontinuity. The components which will be used in our proposed concept will be a vibration application, module drive card, and the application module, then the alert system, and the vibration sensing module. Pictorially, if I present it, then this is the railway track. We will have a control room from where signals will be transmitted, vibration signals, to a vibration application module drive card. From vibration application module drive card, it will be transmitted to an electromechanical application module. These electrical signals will be transmitted and then they will be converted into the mechanical signals, and then the vibrations will be applied to a vibration application point 300. From there, the vibrations will be transmitted along the track, and if we have a sensor, say 400, it will pick up vibrations in the vibration sensing module. These vibrations will be transmitted to electronic sensing card, and from there back to control room. Now an algorithm will be used to compare the reference signals, which is in a repeated mechanical vibration, with the reference with the signal which will be picked up. And if the conclusion is there is a real fracture, then alerts and SMS will be generated and will be sent to all concerned. The same process will be repeated for the other rail also. How the application of vibrations will be done. So we have an application vibration module. From that, a mechanical interface will be used, which will apply vibrations to the rail. The vibration application module drive card will consist of a microprocessor which will transmit signals to the driver interface, and from driver interface it will be applied, transmitted to vibration application module. The signal which is transmitted to the vibration application module will also be stored in a memory and transmitted to the control room using a communication interface circuit and an external communication line. All these will require a power source also. For picking up the signal, again you have an application interface, vibration sensing interface, which will pick up the mechanical vibrations and will transmit to the vibration sensing module. This vibration sensing module will transmit the signals to vibration sensor, those mechanical sensors. They will be converted into electrical analog signals. Then analog signals will be converted into digital signal, transmitted to a microprocessor, and then signals will be stored in the memory and will be transmitted to the to the control room through an external communication line. This will be compared there, vibration reference with the reference signals, and be using an algorithm. A decision can be taken whether there is a discontinuity in the track or not. Now, the advantages of proposed concept. It can determine the fractures on a real-time basis. There is no, because as I told you in the case of a railway vehicle, there is no requirement of a rail vehicle. It doesn't require any traffic block. If you install the sensor points at say 500 meters apart, then you can use the reference signals to identify the exact location also. In case of USFD detection equipment, the inadequacy is that it is point-based, whereas it is not point-based, it is throughout the track. It covers a large area. This fracture data can be integrated into the track management system module also. It can detect surface cracks as well as crack anywhere in the body of the track, or body of the rail. The system is made intelligent by using a reset time. Normally at around 7 p.m. when all maintenance activities are over, we reset the system. And some comparisons are there with reference to UBRD. In case of UBRD, we use high frequency ultrasonic waves, whereas in this it will be mechanical waves only, low frequency vibration. In case of UBRD, the detection is at an interval of 15 minutes, whereas in this case it will be a continuous detection process. In case of UBRD, the movement of train causes disturbance to the system and it cannot be work in that particular period. But in case of mechanical vibrations, in fact, movement of train will be an added feature which will help in identify defects in a better way. So it will add. So it has a huge potential. We can say that the reliability of UBRD probably is not good because on Northern Railway we have not found it very successful. The results are not encouraging, whereas if this system is tried, probably we can have a better and more reliable system. Thank you.
Thank you, Mr. Mittal, for the paper on new concept of detecting the rail fracture using vibrations. And I wish you and your other team member, Mr. Parth, for a successful completion of the project so that it can be implemented on Indian Railways. Now we come to the next paper, which is on IT enablement and leveraging technology in engineering department on IR. No, this paper will take in the end. Now I call upon Mr. Rajesh Prasad for his paper, execution of 680-meter long tunnel ensuring safety of the adjoining rail tunnel with controlled blasting and monitoring in mass affected zone of SDN route of Southeastern Railway and experience and overview.
Good morning, everybody. Actually, I am CPM A.K. Roy. In place of Mr. Rajesh Prasad, I am presenting the paper here. I am in RVNL. So this is a paper related to the execution of 680-meter long tunnel ensuring safety of the adjoining tunnel, because there is a very close tunnel here and we have to construct the third line tunnel. So that is a very big challenge, and the tunnel blasting was done through the controlled blasting methodology and with a monitoring system to the existing tunnel. So this is the paper actually. So in brief, actually the project is 27.5 kilometer third line, and this is in a very challenging area, IPWE affected, means moist area, fully moist area. And the second challenge was, technical challenge was the construction to be done within a very close proximity of 31 meters center to center. The first phase was commissioned in 2016, 11.6 kilometer, and 15.9 kilometer. The remaining is now to be commissioned because tunnel was the most critical here. The background of this work was that the work was sanctioned in the year 1992, but due to these challenges, the work was frozen by board, and again the work was defrozen. And when RVNL became the organization here parallel to the railway, they transferred the work, this challenging work, to the RVNL, and the work thus started from 2011. When we passed 1 year after execution of the work, a very setback was happened, और ये बहुत बड़े बड़े इसमें आप देखेंगे हिंदी पेपर्स में सारे में जो है तो all the machineries were burned at tunnel site. More than 10 crores were lost to the agencies, and within a year, and he was even not approached to the tunnel face. So that was a challenge. Again, with the help of the railway and the state government, security forces were deployed there, and the work again resumed after a stopgap of around 2 to 3 months. So the main feature of the work is the curve in tunnel alignment. The tunnel is in a curve because there is a space constraints there, because it is third line. The tunnel is 1 in 100 gradients. The shape and size of the tunnel is a horseshoe type tunnel, because in the D type of tunnel actually there are frequent failures in the vertical wall because tensions are being created there. So it is modified as a horseshoe tunnel shape, and following the lines where the discussion will be done, the control blasting technique, ventilation shafts, steel reeds, steel fiber reinforced concrete, rock bolts, LED lights and monitoring system. So this is a very simple technique, because it is a very beautiful technique. Can you imagine that in country of Norway, which is a very small country, there are 6,000 kilometers of tunnel, including road and rail. But here, what Ami sir yesterday told that we have only 150 kilometers of tunnel in India. So we have to take the challenges of the making tunnel, and it is a very beautiful technique. Blast and drill and blast is the simplest technique. पूरी माइनिंग, पूरी कोल इंडिया, एवरीथिंग इज डिपेंड अपॉन दिस टेक्निक. हमें इसको पूरे अच्छे तरीके से बहुत ज़्यादा स्तर पे इसको यूज करना है. दैट इज आइए. सो व्हाट इज द सीक्वेंसेस? फर्स्ट यू हैव टू डू द ड्रिलिंग, and then loading. The sequence is there, then blasting is there, defuming, you have to dislodge the material, you have to descaling you have to put the rock bolts here. Before that there is a initial shortcutting, because जब जैसे टनल बनाते हो तो you make a arch actually, and some portion of the arch is very unstable because cracks are generated. So you have to reconnect this unstable arch portion to the original rock mass, so that arch action is transferred to the background of the stable zone. So that is how the full technique depends upon. This is the uncontrolled blasting. Blasting is a huge force, huge force. 1 liter of explosive expand 1,000 times in milliseconds. There is a huge energy. So this is the desired effect, breaking of the rock mass, and the unwanted is the ground vibration reductions, air overpressure reductions be required, the breaking of rock mass into the desired shape. So these are the fallate rocks there, unstable rock. This is the heading and benching is used because we reduce the quantum of blasting potential, blasting amplitude. This is the approach portion. We cut it here by not by blasting, because we are not allowed it by the state authority. It is by chiseling method we remove huge rock mass. I am coming to the main monitoring system. So that is the main here it is base. So this is a monitoring system. It is a very simple methodology. We just measure the peak particle velocity. जैसे कोई blasting होता है, because shock gas are generated, and we divide the total blasting into 10 parts. You find that it is only single blasting, लेकिन वो single blasting नहीं होता है. It is a combination of 10 to 12 number of blastings in a very small milliseconds gap. So a wave is generated, and its velocity, its peak particle velocity is monitored by the monitoring system, very small tool, and such type of signals are being generated. Our requirement is to keep the peak particle velocity of the existing structure, means existing tunnel, within 10 millimeter per second. That's how we designed our control blasting methodology here, and we kept it within the 10 millimeter per second. Thanks to General Manager Southeastern Railway, जब ये tunnel almost 600 meter हो गया था, then we told him, sir, there is a requirement of another 100 meter. Can you help? He presented beautifully this matter to Chairman Railway Board, and Chairman Railway Board in a meeting with Honorable Chief Minister Jharkhand, he allowed for the night blasting, and within the two months of time, we completed our total blasting work. This is how the CRPF and forces are there, and the cost is very low there. It is coming 3.35 lakhs per meter. This is conclusion. Teamwork divides the task and multiplies the success. This is my quote actually. मेहनत इतनी खामोशी से करो कि सफलता शोर मचा दे. पहले आपको हल्ला करने की जरूरत नहीं है, आप काम करते जाइए, अपने आप आपको जो है सफलता मिल जाएगी. Thank you.
Thank you, Mr. Roy, for an energetic presentation on tunneling. The next paper is, I call upon Mr. R. P. Tiwari and Mr. Rahul Singh, Director RDSO, for inspection and monitoring of Indian Railway P.Way present practices and proposed improvements.
Good morning, sir. In the present paper, we have make an effort to summarize the present practices and the improvements which we are going to implement on Indian Railway. Presently, we are monitoring the track under loaded condition. Only track parameters are being recorded. The remaining inspections are done manually under floating conditions. To assess the real need of the maintenance, correlation between reasons and factors contributing to deteriorate the track parameters is essential. Presently, manual inspections is being done for the various level and various type of inspection, ballast and subgrade on the requirement, and all these are given in the chapter 1 of P.Way manual. The present process of a two-stage process, observing the condition of the asset and then decision making. And the decision making is very subjective, and it depends on the knowledge and experience of the individual, because no fixed laid down criteria is available to consider the objectivity. Automated monitoring of track is done by monitoring of track geometry parameters under loaded condition by track recording cards, acceleration measurement by OMS, and preventive monitoring of fail flaws using USFD systems. Why we should adopt the automated inspections? In present practice, the physical track irregularities are measured under loaded conditions, but factors causing the track irregularity are identified and linked manually with a time gap. Quantitative collection, analysis of data during video inspection, and elimination of subjectivity. Video inspection data is correlated with track geometry parameter defects and is available for future reference and verification. Predefined regions and logics to arrive at decision making regarding maintenance and change of asset based on correlation of track defects with condition of track components. Rear window and driver's view video recording for condition monitoring of track features. An initial effort was made long back in 93-94, where analog video recording was introduced in the track recording cars. But at that time, digital video recording was not available, so it was not feasible to correlate the track defects with the track features. Now, with the availability of the digital video recording, it is feasible to stamp track defects and the acceleration defects with the videos. Occurrence of track defects can be correlated with ground features, correlated with the ground features such as point-end crossing, level crossing, bridges, approaches, curve, and curve exit. And the field of view for these cameras can be fixed up to 4.5 meters. Coming to the condition monitoring of the track components using video cameras and laser scanners. These systems are equipped with LED lighting for illumination, laser scanners for detecting three-dimensional defects, high-speed monochrome and color video cameras. A combination of these two are required because some defects are to be monitored by color camera only. Computers with high resolution color monitors and parameters. Typically 9 cameras are used for complete tag component scanning. 2 on the rail top image, 4 sides of left and right rail, and 3 to cover complete ballast and sleeper top view. Now what components we can detect with these cameras? Cracks, longitudinal and transverse. In longitudinal direction, we have capability to measure up to 0.5 millimeter resolution. And in transverse direction, this resolution is 0.1 millimeter. But now we have to analyze and fix our limits, what we want to monitor, because the capability is too much. The area defects above 10 millimeter square can be measured with this system. In addition, sleeper cracks of 2 millimeter into 20 millimeter, misalignment of the sleepers up to 5 degree, more than 5 degree, and different values are there, which we can measure with these systems. But before adopting this, we have to lay down the values of these features, which is essential. Otherwise, there will be so many reports, so many defects will be reported and correct. In addition to this, condition monitoring of turnouts is also feasible with these video cameras. In the conditioning monitoring of the turnouts, in addition to the video camera, we are using existing initial measurement units, which we are using for the measurement of track geometry parameters. Now coming to the Excel box level acceleration measurement system, unattended systems. High frequency and magnitude is there. Acceleration values needs to be fixed through correlation with vertical and lateral track parameters before adopting these systems. Just like the track tolerances, these tolerances are need to be fixed. For this, we are getting a track monitoring system, integrated track monitoring system, which will correlate the acceleration at Excel box level as well as the track parameters. So these values will be fixed before that. Coming to the infringement of maximum moving dimension, in this a 360-degree rotating laser video camera to determine the clearance profile with reference to track axis, uploading of predefined clearance profile, measurement of track level inclination, inspection of tunnels, detection of and reporting of obstacle in predefined MMD envelope, and the obstacle of 10 into 10 mm can be identified with these cameras. Then track bed scanning by ground penetration radar to assess the ballast and the track bed. These GPR technology can be used in the system. Now coming to the advantages of automated systems, quick and efficient inspection with synchronization with track parameters in the same time frame. Throughout inspection in case of inspection of ballast conditions, objective assessment based on well-established logic and predefined values, feasible in almost all atmospheric conditions, feasible of data uploading directly in tag management system instead of manual entry, feasibility for development of asset deterioration model on the basis of historic data, also with introduction of semi-high-speed manual inspection like on foot, and foot and inspection will not be safe. Planning of Indian Railways. We have 16 tag inspection monitoring system having capability of video inspection tag components, video inspection of track features, and acceleration measurement system has been included. 4 integrated tag geometry measurement system
covering all the features are being procured. 40 unattended axial box level acceleration measurement systems, service contract for inspection of ballast and subgate with ground penetration radar, 6 self-propelled vehicular USFD testing systems, and turnout parameter measure system can be integrated with the existing track recording car by installing additional cameras only using same IME. Thank you, sir.
Thank you, Mr. Tiwari, for a very comprehensive overview on what the various track inspection systems available on Indian Railways and what we are going to adopt in future. And for the sake of audience, I can tell you that Mr. Tiwari is one person in RDSO who can be relied upon as far as